Hello everyone. Welcome to third session of solar photovoltaics. In this we will be covering everything in detail about PV cells, modules, and configurations. This course is presented by B. S. Govardhan. The PV value chain. Manufacturing process. Step 1, sand. It all starts with the raw material, which in our case is sand. Step 2, ingots. Step 3, wafers. Step 4, solar cells. Step 5, from solar cell to solar panel. Step 6, testing the modules. Outline of course. Introduction regarding solar spectrum, photons and semiconductors, basic physics of solar cells, PV cell construction, PV array row spacing. Important terminology. STC, standard test condition. Solar air mass. Current V/S voltage curve. Response to solar irradiation. Response to temperature. Shading. Function of inverter. Inference. Solar spectrum. The energy that reaches the Earth is known as solar radiation. Although the Sun emits radiation at all wavelengths, approximately 44% falls within visible light wavelengths. The electromagnetic spectrum represents the complete range of electromagnetic radiation. Visible light, infrared, ultraviolet, X-rays, and radio waves. Knowing about solar spectrum helps us to choose type of solar cell. Some solar cells may have a good performance at short wavelengths, while another type of cell may be better at long wavelength. Photons and semiconductors. Photons. Photons are energy in the form of light and electromagnetic radiation. They have no charge and no mass. Energy from the sun hits the surface of the cell, in the form of photons. The energy of photons is converted into electricity by the solar cell. Semiconductors. PV cell is a semiconductor made from a crystalline silicon, Si, material. Semiconductor materials silicon and germanium have a conductivity in between conductors and insulators. Basic physics of solar cells. Silicon, Si, is from group 4 of the period table. When many silicon atoms are in close proximity, the energy states form bands of forbidden energy states. One of these bands is called the band gap, Eg, and the absorption of light in silicon is a strong function of Eg. Radiated energy from the sun has to be captured and then converted into electricity by the photovoltaic effect. Using special cells called photovoltaic, PV, cells. These cells make up solar panels. A solar cell is made of two types of semiconductors, called P-type and N-type silicon. The P-type silicon is produced by adding atoms such as boron or gallium that have one less electron in their outer energy level than does silicon. Because boron has one less electron than is required to form the bonds with the surrounding silicon atoms, an electron vacancy or hole is created. The N-type silicon is made by including atoms that have one more electron in their outer level than does silicon, such as phosphorus. Phosphorus has 5 electrons in its outer energy level, not 4. It bonds with its silicon neighbor atoms, but 1 electron is not involved in bonding. Instead, it is free to move inside the silicon structure. Near the junction of the two layers, the electrons on one side of the junction, N-type layer, move into the holes on the other side of the junction, P-type layer. This creates an area around the junction, called the depletion zone, in which the electrons fill the holes. When sunlight strikes a solar cell, electrons in the silicon are ejected, which results in the formation of holes, the vacancies left behind by the escaping electrons. If this happens in the electric field, the field will move electrons to the N-type layer and holes to the P-type layer. If you connect the N-type and P-type layers with a metallic wire, the electrons will travel from the N-type layer to the P-type layer by crossing the depletion zone and then go through the external wire back of the N-type layer, creating a flow of electricity. PV cell construction. Low iron glass. Polymer layer, EVA. Anti-reflective coating. PV cell consisting of contact for electricity. Emitter, N-type Si. Base, P-type Si. Contact for electricity. Back polymer layer. Converting light into electricity. Photons reach emitter layer. Energy from the photons releases electrons from N-type silicon layer. Electrons are attracted to base region. Holes in the base are then attracted to emitter region. This is a flow of electricity. Electricity will flow through the two contacts. Same principle as a diode. One PV cell is approximate 150 mm in diameter. In bright sunshine it produces 0.45 volts of D.C. One module is an array of approximate 30 cells, connected together in series/parallel for desired voltage. Lifespan is about 25 years. Cost varies. Solar panel ratings. Max voltage in single PV cell is approximate 0.4 volts, DC. Current depends on sun intensity. Max of 2.5 ampere. Average voltage from a module is 20 volts, DC. The graph shows characteristics of voltage and current of a PV module. It is clear from that as the incident solar radiation level increases, the maximum current for a PV array also increases and has no significant effect on voltage when the temperature remains constant. Here we can see types of solar cells. Monocrystalline. Monocrystalline solar panels are generally thought of as a premium solar product. The main advantages of monocrystalline panels are higher efficiencies and sleeker aesthetics. To make solar cells for monocrystalline solar panels, silicon is formed into bars and cut into wafers. These types of panels are called monocrystalline to indicate that the silicon used is single crystal silicon. Because the cell is composed of a single crystal, the electrons that generate a flow of electricity have more room to move. As a result, monocrystalline panels are more efficient than their polycrystalline counterparts. Polycrystalline. Polycrystalline solar panels generally have lower efficiencies than monocrystalline options, but their advantage is a lower price point. In addition, polycrystalline solar panels tend to have a blue hue instead of the black hue of monocrystalline panels. Polycrystalline solar panels are also made from silicon. However, instead of using a single crystal of silicon, manufacturers melt many fragments of silicon together to form the wafers for the panel. Polycrystalline solar panels are also referred to as multicrystalline, or many-crystal silicon. Because there are many crystals in each cell, there is less freedom for the electrons to move. As a result, polycrystalline solar panels have lower efficiency ratings than monocrystalline panels. Thin film. A thin film solar panel is made of thin films of semiconductors deposited on glass, plastic, or metal. The films are incredibly thin, often 20 times thinner than crystalline silicon wafers. This makes thin film solar panels flexible and lightweight. If the thin film cells are encased in plastic, the product could be flexible enough to mold to a roof's shape. When glass is used, thin film panels are more rigid and heavier. There are three common thin film divisions: amorphosilicon, cadmium telluride, and copper indium gallium selenide. Physical identification of solar panels. If you see a solar panel with darker blue or cells, it's most likely a monocrystalline panel. Unlike monocrystalline solar cells, polycrystalline solar cells tend to have a bluish hue to them due to the light reflecting off the silicon fragments in the cell in a different way than it reflects off a pure monocrystalline silicon wafer. The biggest differentiating aesthetic factor when it comes to thin film solar panels is how thin and low profile the technology is. As their name suggests, thin film panels are often slimmer than other panel types. This is because the cells within the panels are roughly 350 times thinner than the crystalline wafers used in monocrystalline and polycrystalline solar panels. Comparison of technologies used in photovoltaic generators. Efficiencies. In fact, monocrystalline solar cells are the most efficient of all. Efficiencies have been documented at upwards of 19%. Polycrystalline solar PV system operated at a 15% efficiency. Again, this is due to the fact that the material has a lower purity. While many variations of thin film products exist, they typically achieve efficiencies of 8.5 to 15%. Cost. Of all types of solar panels, monocrystalline panels are likely to be the most expensive option. This is largely due to the manufacturing process. Because the solar cells are made from a single silicon crystal, manufacturers have to absorb the costs of creating these crystals. Polycrystalline solar panels are typically cheaper than monocrystalline solar panels. This is because the cells are produced from silicon fragments rather than a single, pure silicon crystal. This allows for a much simpler cell manufacturing process, thus costing less for manufacturers and eventually end users. The overall cost of a thin-film solar panel installation may be lower than installing a monocrystalline or polycrystalline solar panel system due to additional labor requirements. Amorphous silicon has 8.5% efficiency. Cadmium telluride cells have efficiency levels result in a range of 11%. Copper indium gallium selenide cells have demonstrated the most promise with respect to their efficiency levels that range from 15%. Somewhat comparable to crystalline technologies. Important technology. STC, Standard Test Condition. Standard test conditions and are the industry standard for the conditions under which a solar panel are tested. By using a fixed set of conditions, all solar panels can be more accurately compared and rated against each other. There are 3 standard test conditions which are: incident radiation 1000 watt per meter square, air mass AM 1.5, cell temperature 25 degrees Celsius, solar irradiance. Solar air mass. The air mass is the path length which light takes through the atmosphere normalized to the shortest possible path length, that is, when the sun is directly overhead. The air mass quantifies the reduction in the power of light as it passes through the atmosphere and is absorbed by air and dust. This number is minimized when the sun is directly above, as the light has to travel a minimum distance straight down, and increases as the sun goes farther from the reference point and has to go at an angle to hit the same spot. Parameters used in PV cells. Maximum power. Maximum power is peak power generated by the PV panel. Maximum power current. The current at which maximum power is produced by a solar panel is called maximum power current. Maximum power voltage. Voltage at maximum power is the voltage at which maximum power is available from a photovoltaic module. Most solar panel manufacturers will specify the panel voltage at maximum power. This voltage is typically around 70 to 80% of the panel's open circuit voltage. Open circuit voltage. The open circuit voltage, VOC, is the maximum voltage available from a solar cell, and this occurs at zero current, open circuit. The open circuit voltage corresponds to the amount of forward bias on the solar cell due to the bias of the solar cell junction with the light-generated current. Short circuit current. The short circuit current is the current through the solar cell when the voltage across the solar cell is zero. Voltage versus current at constant temperature. The graph is called in-4 curve, and it refers to the module's output relationship between current, I, and voltage, V, under prevailing conditions of sunlight and temperature. In a solar cell, the parameter most affected by an increase in temperature and irradiance. Voltage. Theoretically, every solar panel has multiple IV curves, several of which are shown for one particular module, one each for all the different combinations of conditions that would affect the STC rating parameters above temperature, air mass, irradiance. That's a lot of possible graphs. A higher irradiance level is more beneficial than higher temperatures when it comes to power output. Ideal conditions would have a very high irradiance level and low temperature, but unfortunately such scenarios are very hard to achieve anywhere in the world, as solar irradiance levels and solar temperatures are very much so dependent on each other. You can see from the illustration that this module loses voltage as the cell temperature increases. That effect is common to all crystalline modules. VI characteristic curve. The graph shows the current voltage characteristics of a typical silicon PV cell operating under normal conditions. The power delivered by a solar cell is the product of current and voltage. If the multiplication is done, point for point, for all voltages from short circuit to open circuit conditions, the power curve is obtained for a given radiation level. With the solar cell open circuit, that is not connected to any load, the current will be at its minimum, 0. And the voltage across the cell is at its maximum, known as the solar cell's open circuit voltage. At the other extreme, when the solar cell is short circuit, that is the positive and negative leads connected together. The voltage across the cell is at its minimum, 0, but the current flowing out of the cell reaches its maximum, known as the solar cell's short circuit current, or ISC. There is one particular combination of current and voltage for which the power reaches its maximum value at imp and VMP. This is the maximum power point, or MPP. Therefore, the ideal operation of a photovoltaic cell, or panel, is defined to be at the maximum power point. Open circuit voltage response to solar irradiance. The short circuit current and open circuit voltage extracted from IV characteristics are shown for sun irradiance ranging from 0 to 1000, where ISC follows the solar power linearly. VOC increases more rapidly from 0 volts to 0.6 volts in the 1 to 100 irradiance, then slowly saturates as the concentration further increases. Response to temperature. Photovoltaic modules are tested at a temperature of 25 degrees Celsius, STC. And depending on their installed location, heat can reduce output efficiency by 10 to 25%. As the temperature of the solar panel increases, its output current increases exponentially, while the voltage output is reduced linearly. In fact, the voltage reduction is so predictable that it can be used to accurately measure temperature. As a result, heat can severely reduce the solar panel's production of power. The best way to determine your panel's tolerance to heat is by looking at the manufacturer's datasheet. There, you'll see a term called the temperature coefficient, Pmax. It tells you how much power the panel will lose when the temperature rises by 1 degree Celsius above 25 degrees Celsius STC. Series parallel connections. In series connection of cells, the voltages of each individual cell adds up, the current remaining the same. You connect solar panels in series when you want to get a higher voltage. In parallel connection of cells, the voltage across the cells remain the same, the current in each individual cell add up. You connect solar panels in parallel to get higher current. When designing your solar system, a critical balance of voltage and amperage needs to be achieved for it to perform at its best. This is where mixing parallel circuits with series circuits is beneficial. Shading in PV cells. According to Kirchhoff's current law, all the cells connected in series in a string will have the same current. When one cell is shaded, the individual current in the cell drops. The cell tries to increase its current output to equal the current in the network, and goes into reverse bias in the process. The cell operating in reverse bias requires more energy. This produces a negative voltage and increased heat dissipation. Due to imperfections in the cell, the temperature increases in some parts of the cell. This leads to a hot spot in the cell, thus damaging the cell. Figure A shows unshaded cell, which gives 100% output. Partially shaded cell, where the output current and voltage are directly proportional to the illuminated area of cell. Shaded cell does not generate any output. Figure B shows How shading just 1 out of 36 cells in a small solar module can reduce power output to 0 to 50%. When a solar cell is shaded, the current through the entire string is reduced. This prevents the unshaded cells from operating at maximum power. Therefore, only a small amount of shading can have a dramatic effect on the power output of a solar panel. Figure C shows gradual decrease in the output voltage of module as the shading on it increases. Figure D shows solar panels in partial shade. Using diodes is one of the approach to reduce shading losses. Diodes are used in parallel with a string of cells. Current flows through the forward bias diodes, when the cells are switched to reverse bias due to shading. This reduces the effect of shading. Bypass diodes are devices within a module that allow the current to skip over shaded regions of the module. By utilizing bypass diodes, the higher current of the unshaded cell strings can flow around the shaded cell string. However, this comes at the expense of losing the output of the cells that are skipped over, shown in Figure 1. Although it would be theoretically ideal to have a bypass diode for each solar cell, for cost reasons a typical solar module will have 3 bypass diodes, effectively grouping the cells into 3 series cell strings shown in Figure 2. For instance, a 36-cell module will typically have 1 bypass diode for every 12 cells. A DC optimizer adjusts its output voltage and current to maintain maximum power without compromising the performance of other modules. A collection of PV modules is called a PV panel, and a system of panels is an array. Arrays of a photovoltaic system supply solar electricity to electrical equipment. Cells are connected in series to form a module. Modules are connected in series to form a string. Strings are connected in parallel to form an array. Module cabling. Solar cables interconnect solar panels and other electrical components of a photovoltaic system. Solar cables are designed to be UV resistant and weather resistant. Special extension cables should be used to connect the positive and negative cables from strings to the generator connection box. Depending on the power output of the modules, PV cables with cross-sectional areas of 2.5 square mm, 4 square mm and 6 square mm are usually employed. The DC cables between the modules as well as between the generator connection box and solar power inverter are 2 core cables, a current carrying usually a live red wire, and a negative blue wire, both are typically surrounded by an insulation layer. Inverter. String inverters. String inverters are a distributed architecture for solar plants. They're small, and each unit converts a much smaller amount of power than a central inverter. Since string inverters are converting less power for fewer panels. If one string fails, the whole array's energy is not lost, just the power from that string. Central inverters. Central inverters centralize the plant's power into one place. String combiners connect wires from each row of panels together, then recombiners combine the output of the string combiners together to feed into the central inverter. Central inverter units are physically much larger than string inverters, use longer wires and can convert more power per unit. Contrast that with a central inverter, where much more power is lost if one goes down. The larger the scale, the greater the savings. Since the upfront cost of string inverters is greater and the logistics of installing so many of them are more complicated on projects size 10 MW and larger, central inverters will likely continue to win on very large projects, especially at a higher voltage. Arrangement of PV arrays on metal structure. Mounting structures support solar panels on the ground, or on the rooftops. Mounting structures are usually made of steel, which is galvanized for protection against corrosion. Lightweight structures could also be made from aluminium. These structures help panels to rest comfortably, prevent from being damaged and more importantly position them at precise tilt angle to harness maximum sun's energy. There are 5 basic types of mounting structures, of which 4 are fixed angle types and 1 variable angle type. Roof mounted racks. Ground mounted racks. Top up pole mounted racks. Side up pole mounted racks. Tracking system mounted racks. Decentralized inverter concept. The PV plant's flexible design possibilities and simple installation are notable advantages of PV projects with a decentralized structure. Benefits. Maximum flexibility in plant design with regard to module types and their arrangement. DC side, installation close to modules with low installation costs. Low transportation costs. Easy transportation even in difficult ambient conditions. Fast installation, many assembly options without additional expense. PV power plants with a decentralized structure enable quick installation of the individual string inverters and make good use of the space available by factoring in location specifics. Central inverter. In the planning phase of a centralized PV power plant, the primary focus is on reliable information about the anticipated system performance and whether the PV project is future-proof. Benefits. Easy to simulate through use of a model. Low system price. Clear and dynamic system performance. Cost-effective communications network with only a few devices. Proven technology for plants up to 700 MW. Higher control dynamics. Future viability with regard to grid management services. Standard transport of inverters by truck. Simple construction. High energy yields, low system costs and future viability are benefits of PV power plant projects with central inverters. Microinverters are set up in the opposite manner as a string inverter. Solar PV systems with a microinverter have an individual microinverter attached at the side of each solar panel. Whereas string inverters send energy from every panel to a single inverter, a PV system using microinverters converts the DC solar energy to AC energy on the spot. Advantages. Poor performing panels don't bring down the production capabilities of the whole PV system. Easy to identify when an individual panel is flawed and in need of maintenance or replacement. Disadvantages. A costlier option than string inverters. Maintenance of microinverters is complicated by the fact that they are located on the roof. Thank you. For any queries, visit our website www.nirvanafoundation.com.